Alright, so I'm trying a little podcast here. Gotten some questions about the project. We're going to talk some more about this on Friday, but I thought I'd go ahead and take a whack at it at the moment. Also, this somewhat relates to some of the issues you saw on the test and a few of the homework problems we've had. In fact, I'm going to pick on a particular problem related to one of the homework ones so that we can look at it. So, let's consider a system dy dt equals, and then our matrix can be A, B, minus B, A, and then times y. And so we'll call this guy capital A like we've been doing. And we want to characterize what's going on. Now the trick here is we're not allowed to choose values for A and B. We want to leave this as general as possible. And then we're going to find out, well, maybe when A is bigger than some number, something happens, or when B is bigger than some number, something else happens. And so then we're going to have kind of a plot in the A-B plane of what the behavior of this system is, depending on the values of A and B. So it's somewhat like what you have in the project, just a little simpler, actually. Okay, so let's take a crack at this here. First job, here's A, so A, B, minus B, A, and first job, of course, to get the characteristic equation, so determinant of A minus lambda I, and this is going to give us, let's see here, so determinant of A minus lambda, B, minus B, A minus lambda. Okay. And so this should be A minus lambda squared minus, and then let's see here, that should be a minus B squared. Okay, so this will be lambda squared, and then we'll have a minus 2a lambda, and then plus a squared plus b squared. And of course we're going to set this thing equal to 0, and now solve for lambda. Alright, now this is a quadratic equation, so it should be easy to solve, so you could complete the square if you really wanted to, or you can use the quadratic formula, and that'll do it for us. So let's see what we get when we do that. And then this is where we're going to really be able to get the characterization determined by the values of A and B. Okay. Alright, so now finally, let's see here. If we use a quadratic formula, we have 2a plus or minus the square root of 2a squared. So that's 4a squared minus 4 times a squared plus b squared. And all of that over 2a. Okay, so I need to fix this up here. Alright. So we can simplify this. So really what you get is A, and of course 4a squared. If you look right here, you got your 4a squared minus 4a squared, so that'll be 0, and so then you end up with minus 4b squared underneath the root. So you got a 2a plus or minus square root of minus 4b squared all over 2. Whoops, I made some typo here. Sorry, we did not. Our coefficient over here should be 1 for our... Alright, don't know why it's not letting me erase, but this should be a 1 here. Should not be an 8. Okay, so when you simplify this, you're just going to get A plus or minus I times B. Okay, now So the game now is what kind of behavior to get. Well, we know that the behavior all depends on the values of these eigenvalues. So what happens? Well, for example, when b is 0, we know that we have the repeated case. That's kind of something simple. We know when b is not 0, we're in the complex case, and then we got to figure out what's going on there. Okay, so if b is not 0, so now the question is, do we have a spiral sink, a spiral source, or a center? Now, one thing to note here while we're sitting here is that this b right here came from back over here, and that came from this part underneath the root. And you may recall from some previous life in pre-calculus that is called the discriminant, and so that really is determining the nature of the roots here. So really a lot of what's going on here hinges on the discriminant, so that's really critical. So you got to understand this discriminant guy, and this is very true of the project they're doing. That's really a big focus, because you can see when that discriminant is 0, that's this case here where you have repeated eigenvalues. This guy drops out if that's 0, and you'll end up with a repeated eigenvalue case. Okay, so that's interesting. Now back to our complex case here. If b is not 0, then we definitely are in the complex case, and then we have to look over here at a. So we get another, so we're going to look at b not being 0, and then what is the situation then? Well, depends. If a is bigger than 0, then we're going to have spiral source. If a is less than 0, so that's the real part, a, so that's spiral sink. And a equal to 0, of course, this is a center. Alright, so this is pretty good. We got a pretty good jump on things, and now we just need to plot this in the AB plane. Alright, so here I have set up the AB plane for you here. So let's see here. Alright, this is vertically here, there's the B axis, horizontally here is the A axis. Now one thing we know is that when b is 0, we have the repeated case. So that's a height of 0 there. So all along this axis here we have the repeated case. Now we know when b is not 0, we get these other cases that depend on a. So for example, when a is less than 0 and b is not 0, we have a spiral sink. So that's both regions that's separated by this funky repeated case here when a is 0, but as long as a is not, when b is 0, as long as b is non-zero and a is over here on the negative end, we have a spiral sink. On the other hand, if a is positive and we stay away from the height of b equals 0, then we have a spiral source. And of course the interesting, kind of unusual case, the boundary case between spiral sink and spiral source, is where a is equal to 0. And we have a center on either side of this funny repeated case. So now you see that we have complete understanding of the situation. You give me an A and a B for this particular matrix. So this matrix this only works for our particular matrix that looks like A, B, minus A, B. So if the matrix has that particular form, this form, oh, whoops, that is definitely not correct. Sorry about that. Nuts. I seem to have gotten rid of my eraser some here. Okay, this should be a B here and an A here. My apologies. And so, as long as we have this form, if you tell me A and B, then I can tell you exactly which kind of behavior we're going to have. So let's have a particular example maybe here. Okay, so I'm going to come down in the corner here and draw an example matrix. So let's say we have -2 here, -2 here, and then we have 3 here and -3. Now I've fit the form. You can see that I fit the form because I have A is -2 and B is 3, so down here you have a -3. So now I want to look where A is -2, so that would be stepping back over this direction, and then B is 3. So I'm guaranteed that my behavior for this guy is a spiral sink. So, so I know that story just from this characterization. So there you go. So that guy's a spiral sink in that particular example. So you're doing something similar with your lab. The matrix is a little more complicated and the results will be more complicated, but again, you're going to use the quadratic formula. You're going to look at the discriminant and kind of piece out all the behavior. You will have all behaviors, not just these few here that this particular setup has, but you're going to see all the different behaviors. Alright, I'll see you on Friday. We'll talk about this some more.